In this video, we're going to be talking about limits. In the last section, we saw how the idea of limits arises from the tangent problem. Now we will turn our attention to the general concept of a limit and the ways in which we compute them. The limit process involves examining the behavior of a function near a given value that may or may not be in the domain of that function. When dealing with limits, you are considering the behavior of the function around a particular value, not what is going on at the value itself. So here's the definition of a limit. We write the limit as x approaches a of f of x is equal to L if we can make the values of f of x arbitrarily close to L by taking values of x sufficiently close to a. The limit of a function is simply describing the behavior of the function values around a particular x value that may or may not belong to the domain of f. The following statements are equivalent. The limit of f of x as x approaches a is L, f of x approaches L as x approaches a, and here's the shorthand notation with arrows. Let's take a look at a graphical approach to limits. Example 1 says graph the functions, then use them to find the requested limits. So in part A, we are asked to find the limit as x approaches 3 of the function x plus 2. Now this here, x plus 2, is a linear function. And so the way that we would graph that, we know that it has a y-intercept of 0, 2, and then the slope is 1. So I would go up 1 unit and right 1 unit to get to the next one. And I will go ahead and connect those to form a line. All right, so I have my line graphed, and this is a cool analogy or a cool trick to think about limits, at least using their graphs. So we know that we're approaching the x value 3, which is right here. And what you can do is you can draw two people that are, imagine that they're walking along the x-axis and they're both getting closer and closer to x equals 3 on the x-axis. And both of these people, they are holding balloons. And these balloons are only moving along the function's graph or the curve. And so if the balloon is moving closer and closer to here, we're asking ourselves, we can think about the limit as being the y value that the balloon is approaching and getting closer and closer to. So in this case, x equals 3, if I were to plug that into my function, we can see that the balloons are approaching this ordered pair right here, and the y-coordinate of that ordered pair happens to be 5, and so it turns out that this limit is equal to the number 5. In part B, we want to take the limit as x approaches 3 of the rational function x squared minus x minus 6 all over x minus 3. I'm going to take that function and I'm going to rewrite it. Notice that I can factor the numerator, and the numerator factors into x minus 3 times x plus 2, and then I still have x minus 3 in the denominator. Now, notice that they share a common linear factor, and now we can write this as x plus 2, although something that's really important is to note, in order for these things or these functions to be equal, they must have the same domain. And so we can't say that they're equal unless we make the caveat that x cannot equal 3, because that x value of 3 was not included in the domain of that original function, because if I plugged in 3 into this x value, I would get division by 0. So now, putting this together, it turns out that this limit is equal to the limit as x approaches 3 of x plus 2. Now let's graph that function that we originally had, this one here, because we were able to see that that was also a linear function. It was the function x plus 2, where x cannot equal 3. And if that's the case, that just means that we have a hole at the ordered pair 3, 5. So here my y-intercept is 0, 2. And then here I'm going to have a hole. And so my graph is going to look something like this. And we can still use the balloon analogy here. So here's x equals 3. I have my person on this side, and they're getting closer and closer to x equals 3. Same thing on this side. This person is getting closer and closer and closer to x equals 3 from the other side. And the balloons, they're getting closer and closer to the location of my hole here. And even though this is not part of my function's graph, the location of that hole still has the ordered pair 3, 5. And so this limit here is equal to 5 as well. Now, you may be asking yourself, in part A of this, did we really have to have a graph? Because as you can notice, if I plugged in 3 here, 3 plus 2 is equal to 5. But notice that we couldn't take that approach in part B, because if we had plugged in 3, we would have had division by 0. So to answer the question, could we just plug in the x value that's being approached? We can sometimes, but not all the time. And we'll explore later when we are able to do that. So here's the definition for one-sided limits. I will let you read over those, but essentially in the balloon analogy, a one-sided limit just means that you're only looking where the balloon is approaching on one side of that x value. And if you have this notation here, this kind of looks like an exponent, but it's just a superscript. This means that the limit, we're taking the limit as x approaches a from the left-hand side, which means that we are approaching a from smaller values of a. And then here, if we have this plus sign in the superscript, that means that we're approaching it from the right-hand side or from values that are greater than a, and we'll see some examples of that in just a moment. And in this purple box, we have an important note that says if the limit from the right is not equal to the limit from the left, we say that the limit does not exist, and often we will just write capital D N E for a shorthand notation of does not exist. Let's go ahead and take a look at some examples of one-sided limits. Example 2 says, below is the graph of a piecewise function f of x. Use it to find the specified limits or values. In part A, we want to find the limit as x approaches 3 from the right-hand side of our function. So, from the right-hand side, let's first find x equals 3, which is right here. That means that we have a little person on the x-axis, and in this case, notice that the balloon is kind of going underneath the ground. So pretend it's a magic balloon, but because our function is below the x-axis there, so this person is walking and they're getting closer and closer to x equals 3. As that happens, the balloon is approaching this point right here, and let's see what y value that is. We're going down 1, 2, 3, so this y value here is -3. So as we are taking our x value to be closer and closer to 3 from the right side of 3, so think of like 3.01, 3.001, what's happening to the y value is we are approaching -3. In part B, we are approaching, or we're calculating the limit as x approaches -7 of our function. So notice that there's no superscript. So this is, I typically call it like an overall limit, which means that we're approaching -7 from both sides. So this person's getting closer here. This person is getting closer on this side. So as they're walking closer and closer to -7, both of the balloons are kind of going upwards, and the position that it's approaching is this ordered pair right here. And so the y value that's being approached is 1, 2, 3, 4, 5. This is 6. So for part B, our answer is 6. In part C, we are finding the limit as x approaches 3 from the left-hand side of our function. So now I have a person and they're approaching the x value 3, but they're approaching from the left. And so their balloon is here, they're going, and it's also approaching that ordered pair there. So that is also equal to -3, similar to part A. And part D asks us to find the limit as x approaches 3 of f of x, which means now we have someone on both sides, and they're approaching 3. And so on one side, it's going this way, and then on the other side, it's going this way. Notice that they're approaching the same ordered pair, and that ordered pair has a y-coordinate of -3. Okay, so for part E, we are asked to evaluate -3. Notice that this is not a limit. It's just asking what is the y value when we plug in x equals -3. So here's -1, -2, -3. If I go up, that y value is 4. Okay. Part F, we are asked to find the limit as x approaches infinity. Now notice that x is not approaching a number here. Infinity is not a number, it's an idea or a concept. So the way that we visualize this is I have a person, and you can kind of place them wherever, but I'm going to place them here. And if x is approaching infinity, that means that the person is walking to the right, because that's the direction of positive infinity. So they're walking to the right forever. And so my balloon is here. And notice that my balloon is not changing height, because right here, at least for this part of the graph of my piecewise function, this is constant. It's not changing height because it's a horizontal line. And so it's staying that height forever. So that balloon is approaching the y value of, this is 7. So here we have that limit is equal to 7 for part F of this question. Okay, so in part G, we want to find the limit as x approaches -1 from the right-hand side. So here is x equals -1. That means that my person is here, and they are approaching -1. They're getting closer and closer and closer and closer, and my balloon is here, and as they're approaching, my balloon is approaching this ordered pair right here, which has a y-coordinate of -3. So here I will put -3. Now we want to approach 6 from the left-hand side. Okay, so I've highlighted x equals 6, and that means my person is here. Here's my balloon, and they're getting closer and closer to x equals 6. The balloon is going towards this ordered pair here. Even though there's an open circle or a hole at that location, remember, we don't care where the function evaluates to or what the y value is. We only care about where the balloon is approaching, and it's approaching this ordered pair right here, again, even though there is a hole there, and the y value of that hole is 0. So that's going to equal 0. Okay, in part I, we want to take the limit as x approaches -infinity. So here I have my person. If the person is approaching -infinity, that means that they're walking to the left forever. And so here is my person. They're walking to the left forever. The balloon keeps having like a downward trajectory, meaning that the y value that we're going to is -infinity because it just keeps going down forever. Okay, in part J, we have the limit as x approaches -4. So I have my little person here. They are approaching -4 from the left-hand side. And then here I have my person with my balloon. They are approaching -4 from the right-hand side. And both of these balloons are approaching this ordered pair right here. And it looks like it's about halfway between these two y values. So I'm going to say that this is 4.5. And we will say that our limit is 4.5 here. Now, part K, we are asked to evaluate f of 6. Again, here was our x value 6. Notice there's a hole there, but there is a closed circle here, meaning that when I plug in 6 into my function, my output value is 7. So this is equal to 7. Okay, now we want to take the limit as x approaches 6 of our function. So I'm going to go ahead and erase a little bit. Notice that in a previous part, we've already calculated the limit as x approaches 6 from the left-hand side, but it doesn't look like we calculated the limit from the right-hand side. So let's do that really quickly. If I wanted to calculate the limit as x approached 6 from the right-hand side, that means that I have my little person here, and they are approaching 6 from the right-hand side. And notice where the balloon is approaching. It's approaching this y value here, which is 7. So this is equal to 7. So the right-handed limit is equal to 7, and the left-handed limit is equal to 0. So notice that as I approach 6 from either side, they're approaching different locations. So the overall limit does not exist, because we said earlier, if the right-handed limit and the left-handed limit are equal to different values, then the overall limit does not exist. And that concludes example 2. Let's now take an algebraic approach to limits. Example 3 says, let's explore the function f of x equals this rational function around x equals 5. What happens if x equals 5? So to answer this question here, what happens if x equals 5? We get division by 0, and so the function's not defined when x equals 5, so undefined. Because 5 is not in the domain of this function. Let's just check that really quickly. F of 5 equals, in the numerator I would have 5 minus 5. In the denominator I would have 5 squared, which is 25, minus 4 times 5 minus 5. And so that would end up being 0 divided by the denominator will equal 0 as well. So let's do this where we have this table here and we're given some x values and we want to find the output value. So I'm going to go ahead and do this by using a graphing calculator and the table feature. All right, so here is my graphing calculator. I'm just going to go ahead and clear my key history so we can see from scratch. If I'm at the home page, I want to go to graph. And then from here, I want to plug in my function. So I'm going to use the fraction feature, and then my numerator is x minus 5, and my denominator is x squared minus 4x, and then minus 5. Okay, so once I'm here, I can push second and then table, and then that will take me to my table. I'm going to go ahead and clear all of these because I don't want those x values. I want to plug in the ones that are in my table. So one of them was 4.9, and then I'll press enter. And then my next value was 4.99. And so notice that I'm getting these output values or these y values. So I'm going to go ahead and do this, follow along on your calculator, and then I'm just going to fill in the table really quickly. All right, so I filled out my table, and I just want to make the observation that these x values, they are getting closer and closer to the number 5, and more specifically, they are approaching 5 from the left-hand side. And these numbers are also getting closer to 5, but these are approaching 5 from the right-hand side. And our goal is to kind of see a pattern in the y values. So these are approaching what seems to be the number 0.16, and I'm going to put a bar over the 6 to indicate that the 6 is repeating forever. And if you can't see that pattern, what you can do is you can go ahead and plug in more numbers into your x values. So you could plug in 4.99999, etc., and see that these are the y values that are being approached. But could we have done this without a table? And the answer is yes. I'm going to explore this kind of like we did in the first example of this video. So I want to take the limit as x approaches 5 of this function, x minus 5 over x squared minus 4x minus 5, and it turns out that we can factor the denominator, so this is going to be equal to the limit as x approaches 5 of x minus 5 over my denominator factors into x minus 5 times x plus 1. And so what happens is this is now equal to the limit as x approaches 5 of 1 over x plus 1. And just like we saw in the first example, I can kind of plug in 5 here, and when I do that, I get 1 over 5 plus 1, which is equal to 1 over 6. And let's just verify that that's what we expected it to be in our graphing calculator, because we want to kind of check, are these the same thing? All right, so I'm going to do 1 divided by 6. And notice that is what we expected. It's 0.16, where the 6 is repeating forever. We have a 7 here because our calculator can't show infinitely many digits of 6, so it has to round it after a certain point. But this is what we were expecting. Let's just also quickly go back to graphing this. If I wanted to graph it, it would look something like this. And I want to explore this around x equals 5. So I'm going to push this button here that says trace, and I just want to go over until my x value is kind of close to 5 and see what the y value is doing. So notice that I'm approaching 5 from the right hand side, and our y value is getting close to 1/6. And then if I approach it from the other side, similar thing is happening. And remember, if you want to change your viewing window, you can press this button that says window here. Our x max is at 14 right now, which is, I think, a little high because we're approaching 5. So maybe I'll change this, my maximum x value, to 8. And then my y min, I will maybe change that to -1. And then my y max, maybe I'll change that to 5. So let's see if that gives us a better viewing window. I think that does. And so I'm going to trace again. And when I get close to 5, notice that when I am at 5 exactly, my y value is showing nothing because it's undefined there and there's a hole. And then it resumes when I go a little bit past 5. Example 4 says evaluate the following limits. Keep in mind that we use the infinity symbol, which kind of looks like a sideways 8, to represent unlimited growth. So here are the 3 limits that we're trying to find. To help us answer, let's answer the following parts. What is the function that we're taking the limit of? So our function is this thing here, and so I'm going to call it f of t is equal to sine of t over t. Part B says, what is the function evaluated at 0? If I were to plug in 0, it would be undefined because we would have division by 0. And part C says, what is its domain? Well, into that function, we can plug in anything other than 0. So our domain is going to be -infinity to 0, union 0 to infinity. And now let's use this table here, because notice that these t values are approaching 0 from the left-hand side, and these are approaching 0 from the right-hand side. So again, I'm just going to use my graphing calculator. Go ahead and pause the video, and you can plug these into your graphing calculator, and I'll show you in just a bit what those output values are. Okay, so after plugging in my t values into my function, I can see that these are approaching the number 1, and so it turns out that this limit here is equal to the number 1. Part 2 says we are taking the limit as t approaches infinity of that same function, sine of t over t. So something important to note if we're kind of thinking about this analytically is, if I am thinking about the numerator, which is the sine function, I know that the range of sine is the closed interval from -1 to +1, meaning that my numerator is just going to kind of bounce back and forth between some number between -1 and +1. But if my t value is going off to infinity, that means that my denominator, I'm plugging in larger and larger values for it, like 1,000,000 or 1,000,000,000 or 1,000,000,000,000. So as my numerator is kind of staying pretty small between some number between -1 and 1, and I'm taking that and dividing it by an extremely large number, that means that my fraction is getting extremely small, and in fact it's going off to 0. And same thing with -infinity, that is also going to 0. So let's just graph this really quickly to see what the graph is going to look like. So I'm going to throw in my fraction. My numerator is sine of x, and then my denominator is just x, and then I'm going to hit graph. And so notice that, well, let's change my window really quickly. I think my y values, I want them to be between maybe negative 1.2 and positive 1.2. Okay, so notice here that as our x value or t value, whatever you want to call it, approaches 0, the y value, we are approaching 1, but notice that it gets kind of shorter as we go off to infinity and negative infinity, and that's because it's approaching 0. So this kind of verifies what we got using our table and thinking about our limits analytically. Example 5 says, find the limit as x approaches 0 of sine of 1 over x by answering the questions below. What is our function? The function that we're taking the limit of is sine of 1 over x, and if we were to evaluate f of 0, this would be undefined because we would have division by 0. So let's use the table to try to answer this question. Notice that these x values here are approaching 0 from the right-hand side, and here our x values are approaching 0. Excuse me, I think I said these are approaching from the left-hand side, and these are approaching from the right-hand side. Okay, so let's think about the unit circle to answer these without using a graphing calculator. Okay, so my goal right now is to evaluate this function for negative 2 over 7 pi, so I've kind of highlighted that here. Notice that this is the same thing as sine of, I want to take the reciprocal, and so I have negative 7 pi over 2, and we're trying to figure out what that's equal to. So I'm going to start here at an angle of 0, and remember, if we're going, or excuse me, if we're plugging in a negative angle, that means that we are traveling in the clockwise direction on our unit circle. So if I go to the next angle at the bottom, that's going to be negative pi over 2. Here will be negative pi. This will be negative 3 pi over 2, negative 2 pi. This will be negative 5 pi over 2, negative 6 pi over 2, and then at the top we'll be at negative 7 pi over 2, and this has a terminal point of 0, 1, meaning that the sine value is the y-coordinate, so this will be equal to 1. Now we want to do negative 2 over 9 pi, but remember we're taking the reciprocal, so that would be the same as sine of negative 9 pi over 2. If I go another quarter turn, that would be at 0, but that angle is also negative 8 pi over 2. And then at the bottom, that would be negative 9 pi over 2. And this has a terminal point of 0, negative 1. So the sine value is the y value, and we'd have negative 1 here. And if I were to fill out this table, these values kind of just switch between negative 1 and positive 1. And so if I wanted to think about where these are approaching, they're not approaching anything because they keep bouncing back and forth between numbers between negative 1 and positive 1. So these do not approach any number. So what does that mean then? Our limit as x approaches 0 of the function sine of 1 over x does not exist. And go ahead and explore a graph to see what that kind of looks like and why it does not exist. So example 6 says, consider the rational function f of x is equal to 1 over x. Find the following limits. I'm going to kind of quickly go through example 6 and 7 kind of together. So here's my graph. If I were to graph the function y equals 1 over x, it looks something like this. It's only going to exist in quadrants 1 and 3. And then in example 7, if I were to graph y equals 1 over x squared, it's going to look something like this. And because 1 over x squared is always a positive number, my y values are always going to be positive, so I'm limited to quadrants 1 and 2. Now go ahead and pause the video, take a moment, and try to fill out these limits, because in just a second, I'm going to reveal all the answers to example 6 and 7. All right, so here are the final answers, and these are the limits. So thanks for watching this video. That concludes this section on limits of functions.